Good morning, everybody. Today we have Frederick Poidevin. Very good. Ooh. Can you switch off your microphone? Switch off? Okay. Frederick did his PhD at the University of Montreal in 2006, and then he performed several postdocs in Toulouse, where he spent 1 year, then in the University of Sao Paulo, 3 years, and finally 2 years in the University College of London. Now, well, very recently he joined the IAC, working in the Quixote team, and he will show us today some results on his polarimetric studies of the SCUBA field.
Thank you. Hi everyone. Thanks for the possibility to give a talk here. Is that working? Can you hear me? Yeah? And I will try to speak a bit louder. That's fine. It's just for the connection, I think. Yeah, I will present you a work about what we call the SCUPOL Catalog. It's a compilation of observations which have been made during a few years at the GCMT in Hawaii. And the plan of my talk is the following. I will give you a short introduction because the topic will be about molecular cloud and star formation regions. So I will give you the context about what is the main issue that we've got to understand star formation nowadays, and how polarimetry can be a very useful tool to constrain magnetic field and turbulence in these regions. So I will give an overview of the catalog, a statistical analysis in the first part, and then in the second part, comparison with MHD simulations that we've performed with my colleagues. So Diego Falcheta Goncalves, Craig Koval, Elizabeth Gigobea Dalpino, and Antonio Maio Magalhães from Brazil. So the question I will address is that star formation occurs in regions which are very cold in the dense ISM. And we don't understand why. I think current studies give a star formation efficiency of about 5%. The gas is converted into stars, and we would expect, if there was no only gravity, with more efficiency for producing stars. But we know that we have a lot of events and turbulence and magnetic fields. So the focus of this talk is about molecular clouds, which are, if we look to the dense ISM, these cold regions where densities are higher than 10 to the 3 per cubic centimeter particle of hydrogen, very low temperatures of about 100 Kelvin, and where the dust mass is about 1% of the gas. And the dust mass actually is not is a small quantity in terms of mass, but it's very important in terms of information it can give us. I will show you. The theory, when people try to understand how molecular clouds form, basically there are two top models. You take the galactic plane, the galaxy, the spiral arms, and there is a gravitational potential. And because of this rotation of the galaxy, fluctuations in the medium will produce molecular clouds. And this could be the main reason for triggering star formation. But we know that on smaller scales we've got a lot of different events because we've got supernovae, explosions, compression of sheets by superbubbles, a lot of flows and turbulence. So basically people take the problem from one side or the other end, you know. Here with the catalog, I will show you different regions and we will discuss a bit more about this. The SCUPOL Catalog, it's do we have a pointer? No, okay. That's all right. The SCUPOL Catalog is so I will show you. The SCUPOL Catalog is so it's a polarimeter. If you look on this plot, on the upper right we see the schematic view of aligned dust grains. And we know that some of the dust grains in the interstellar medium, they are aligned by the magnetic fields. And they will be rotating perpendicular with a small axis aligned by the magnetic field. So this gives us information if we use polarimetry at 850 microns, for example. This will give us indirect information on the magnetic field projected on the plane of the sky. And if we use polarimetry in the visible, which is the schema on the left, we'll see if there is a star behind a layer of dust grains which are aligned by the magnetic field, we can see polarimetry by absorption. So basically, the SCUPOL catalog is looking deep into the clouds because we know that at submillimeter wavelengths, most of the radiation is going through all the medium. And so this was the motivation, one of the motivation of this instrument at the GCMT. And the SCUPOL catalog here is a summary of all the regions which have been observed. It's been re-reduced homogeneously by Brenda Matthews and collaborators in 2009. And that's what we've used, the catalog we've used for this analysis. So we've got one interesting large map of the galactic center, a lot of star-forming regions, some young stellar objects, starless prestellar cores, and bug globals. So basically cold regions. And we have also other objects actually, but I didn't mention everything. And basically the talk will be about the star-forming regions and the molecular clouds. So here it is an example. For those who are not familiar with this, when we have a polarization map here, the pseudo-vector here give us information about the orientation of the magnetic field, because we are probing the radiation emitted by the aligned dust grains. And we've got different intensities that I will discuss more about it. And we can see that we've got nicely aligned structures, sometimes changes of directions. And this gives us information about the medium. And this is, of course, in 2D projection. So one method we can use for analyzing such maps is a method developed by Chandrasekhar and Fermi in 1953. The basic idea was that here we've got a view of the galactic plane, and all the pseudo-vectors are polarimetry data obtained in the visible. So on stars, by absorption of the light by the aligned dust grains, and it gives us information about the magnetic field in the galaxy. So this is a map of the structure of the field as seen in the diffuse interstellar medium. And the basic idea is that because we are into a spiral galaxy, the fluctuation we can see in the magnetic field lines are related to the turbulence. So Chandrasekhar and Fermi developed with MHD equations a possibility to define the intensity on the plane of the sky, so of the magnetic field with each h. If we have an idea of the mean density of the medium, the velocity dispersion of the gas, and alpha is the dispersion of this set of vectors in the plane of the sky. And so with this description, they were able to make an estimate of about 6 milligauss for the diffuse magnetic field intensity as seen in projection. And it's consistent with other techniques from Quasar, I think, and other studies, independent studies. And this method has been transposed to very smaller scale and very denser medium to try to understand star formation regions, or how the magnetic field could act on the formation of stars. And so that's what is explained here. And some simulations have been developed with some correction factors, so it's more technical details. But a lot of people have been investigating this field during the last 20 years, let's say, a bit more, even more. And more recently, to analyze a bit more precisely the polarization maps, in the Chandrasekhar and Fermi formula here, the dispersion is a standard deviation of all the vectors which are in the plane. But we have tools which can, we've got autocorrelation functions. So if we've got a map, we could use the average standard deviation of the vectors, which give us the average fluctuation of the field into the map. But we can also use a autocorrelation function, which means that for different length scale into the map, we look how there is variation of the orientation of the field. And coming from the Shankar, so it's just a refinement of the method. And coming from the Chandrasekhar and Fermi method, it is possible to define this ratio. So the mean turbulent, the intensity of the turbulent magnetic field component divided by the uniform component. Because in general, on large scale, we've got a quite uniform field, but we know that on smaller scale, we've got a turbulent field. And once we've got this dispersion element that I will explain a bit more, with the Chandrasekhar Fermi method, we can have a lot of information about the medium. And so we did this for, so this is technical aspect of the method. And so this is an autocorrelation function when it is applied to a map. We've got for different length scale, for different distances into the map, we've got an estimation of the perturbation of the field. And the B parameter is a key parameter for our analysis. It gave us, in fact, the highest, the value of B, which is the interpolate of the structure function here. And the more turbulent the medium is supposed to be, because we see a very tangled magnetic field. So we did this for all the maps, in addition to defining the average polarization degree and the standard deviation of the distribution of angles. And another important thing that we still don't understand completely, actually, via simulations, it's not been reproduced yet, I think, or it depends of, I mean, not with turbulence. We've got what we call the depolarization parameter. So you can see in this map, on the background, it's the intensity. So it's all the column density. We know that we have more denser regions into this line of sight along the spine of the filament. And in general, in these regions, very, very dense, we've got cores which are forming. Maybe we've got outflows. And people who first study the magnetic fields in those regions with polarimetry in the 3 millimeter, they saw that there is a decrease of the polarization degree, so the length of the vector here, as a function of the intensity. And this is not completely well understood. Maybe it could be because we've got a loss of alignment of those grains when we go deep into the cloud, but it's not completely understood. And but this can be useful for characterizing polarization maps. So we calculated all these parameters: the mean degree of polarization, the turbulent dispersion, and the depolarization parameters for all the regions, star-forming clouds, star-forming regions and molecular clouds mainly. And we see that the mean distribution is between 3 to 10 degrees. So this gives us information about the dust grains efficiency, dust grains alignment efficiency. And we see that there is no correlation here. It's the mean polarization angle of every region, every cloud. And we see that there is no direct, no specific peak. It's even if we could find a very broad one. And this is in agreement with the work by Stephen et al., which shows that the magnetic field into the molecular cloud is maybe not necessarily correlated to the magnetic field into the plane of sky, because the regions will be out of the plane or more dense, or the field has been killed. It's not. It's a statistical result. And so our study just is consistent with their work to check if there was not possible bias, because we've got very different. It's a catalog of sources. So most of the sources are to a few hundreds of parsecs, and the highest at about 10 kiloparsec. Not the highest, the farthest. And so we just wanted to check here if the estimation of our parameters was a function of the distance, for example, or of the number of pixels in the map, of the quality of our sample, and we don't find any specific trend. So we believe that in this sense the statistic and the comparison we are making are homogeneous. And once we've got all those parameters, so it's a bit technical for the moment, but it will be clearer, I hope, later. So what we define from the maps is those turbulent parameter. It's those depolarization parameter, which translates the slope of the polarization as a function of the density. So how the magnetic field sees the density, the medium. And so from a probability distribution function of vectors, for each map, we've got a distribution of vector. We define the mean polarization degree. And we know that there is a dust grain efficiency. So each grain can be aligned more or less efficiently. So we can translate it by this Rydberg parameter. We've got two different philosophies in the literature to describe it. And we've got once all those grains are aligned, because the magnetic field can be tilted all along the line of sight because there is more or less turbulence. We've got a turbulent parameter here. And here we know that we've got in general a uniform magnetic field on large scale. And so this is the inclination of this mean field. And so we see that those parameter P is function of all the parameters inside this equation. So basically the capability to align grain efficiently or not, the structure of the magnetic field, and the injection of turbulence in the medium. So we are not expecting necessarily that we will find correlation between the mean degree of polarization, the depolarization parameter, and the turbulent parameter. So we've checked this, and that I will focus on this plot because that's where we have the most of the largest statistic. And we effectively don't find any correlation between P and the mean degree of polarization and the parameter B, which translates the level of turbulence as seen from the point of view of polarimetry. The same between the depolarization parameter and the turbulence parameter, and the same between the depolarization parameter in this plot and the efficiency and the mean polarization degree. And this was a sanity check. So this gives us information. We are dealing with a level of complexity, and but fortunately, for some regions, we've got also independent measurement or estimate of the magnetic field. So with the Chandrasekhar and Fermi method, I discussed, it is possible to get estimate of the magnetic field in some regions, as on average on the plane of sky. But for some regions, we've got Zeeman measurements of stocks V and I. This is an example in the R21. So it's Crutcher who's done a lot of work during the last 20 years, if not even more. And so we've got interesting catalogs. And we see here it is the density of the interstellar medium. So when it is 10 to the power 21, it's in this range or lower. It is a diffuse ISM. And we can see from Zeeman measurements when we try with this work, we can see that there is an increase of the magnetic field into denser regions. So this tells us something that the field probably is very important in terms of maybe slowing the mechanism or redistributing the turbulence in the medium. And so for some regions, those data have been useful because it's been possible to combine our estimate of the intensity of the field on the plane of sky with Zeeman measurement. And so we've done this analysis for about 8 regions. And this is the line of sight in microgauss intensity of the field as estimated by Zeeman measurements. And with the Chandrasekhar and Fermi method, we've estimated the intensity of the field on the plane of sky. So it was possible with this simple calculation, because we've got an estimate of being to the plane of sky along the line of sight, to get an estimate of the inclination of the field, of the uniform field. And this is a constraint that we've been calculated for those regions. So that was also another interesting piece of information. And this was a sanity check as well. I will go through this. But ultimately, the idea to make all this statistical study, or to extract all this information from the maps, was to explore MHD simulations. The idea is that with simulations we know what we inject into what the physics we use for producing some maps, and how can we compare by retrieving the same parameters from synthetic maps. So for this we've been using some simulations which have been developed by Diego Falseta Goncalves and collaborators. There is most of the physics is explained in this paper of 2008. So we've got the basic isothermal non-MHD equations described here. I won't go through this now, of course. This is an example. So the quality of the map, no, that's okay. We've got, for all the dense regions, we've got an information. This is so we've got a cube, and we compile all the information along the line of sight. In every cell, we estimate Q and U with a polarization efficiency of 10%, which means that we force the system not to have a higher polarization of 10%. We've got the Q and U parameter are weighted by the density of the medium. We also know that for the cubes, the interest of the cube is that if we consider we've got uniform field at the beginning, and we inject turbulence, so there will be a mix of the field lines. But since we have cubes, we can rotate and make maps for different uniform field inclination angles, which can be compared to the information we've got from the data. And so this is related to the parameter and the physics I was explaining before. And I will make a short interruption just to show you some models. Those are the cubes for some slice. So this is the evolution of the magnetic energy if we look at one slice of the cube as a function of time. And so we can see the mix of the energy density. And we've got the same for, so that was magnetic energy, for the column density. And so this is related to the density of the gas. So we see that we've got similar patterns, and so there is correlation between the magnetic energy and the density of the medium. But what we don't exactly know or understand now is that how far with polarimetry we can probe the magnetic field into the medium. And so this is related to the problem we're discussing, because we need to understand how the field acts with turbulence to slow down or stop star formation at some point. And so for comparing with the cubes, because in this, yes, I didn't mention this, but in the modeling there is, so the cubes, they are isothermal because we make the hypothesis that the clouds are more or less around 20 Kelvin, and there is no gravitation included. So what we've done is that for 4 regions that we've studied very deeply for comparison with the simulations, for some maps where we know that we've got cores, we have masked the cores, and we've extracted the parameters that we want to compare with the simulations. And we did that for the 4 regions. And very exciting first result is that for some simulations, when we scale the injection scale at about 10-50 parsecs that we expect from other data, we use the real size of the cloud as seen from the map, because we know the distance of the maps of the cloud, and we know the resolution of the map. So we've produced cubes, very large cubes with a turbulent cascade of energy, as I shown you before. A dissipation scale for turbulence of 10 milliparsec, and it's been possible by so looking in some isolating into a cloud a region similar to the physical cloud in terms of scaling to make estimate of the turbulence regimes. So in other words, we've estimated with the cubes the sonic Mach number, which is the ratio of the velocity of the gas over the sonic speed, and the Alfvénic Mach number, which is the velocity of the gas divided by the Alfvén speed, which is the speed of a magnetic wave into the medium when we've got turbulence, to make things simple. And with these numbers, once the cubes we've isolated some part of the cubes which have been scaled over the clouds, we've been able to define those turbulence regimes for the 4 regions, And interestingly, we are within a factor 1 to 2 with some estimates which are provided by Zeeman measurements analysis and the turbulence of the gas. So that was the first nice surprise actually, because this means that the turbulent cascade from large scale to the envelope of the clouds, the physics seems to be quite close at what we can observe. And as a second step, so we tried to see if we could recover from those specific cubes which are scaled over Zeeman measurements in a sense, even if we were not expecting it will be working so nicely at the beginning. We've investigated how the parameters extracted from the observed map scale with can compare with the one extracted from the simulated maps. And for the depolarization parameters, which I consider a bit, it's how the magnetic fields will see, how via polarimetry we can see that the fields see different density regimes. So since we don't have gravity, and since we are using very simple dust grain models, we are not able to find this parameter to recover it, or it's within a factor of 2. But the interesting part is that one, so I need to explain this a bit. This, for each plot, is a, so we've got a uniform field into the clouds, and you can rotate the field from the simulation. So 0, it's when the magnetic field is along the line of sight, the uniform field. Then we inject turbulence, and we see how the medium evolves. So we can see that the B parameter, which comes from the analysis of the dispersion of the angles into the map, it is very high because we don't see the uniform field structure. Because if there is a uniform field structure, the grains are aligned perpendicularly and rotate, and so we won't see a large degree of polarization. There will be a large mix. But the vectors will take a lot of different direction. But if we go into that direction, when we start to get some uniform field close to the plane of sky, the uniform component of the field dominates. And if we still have turbulence, there will be a mix of the lines, and we can recover it into the maps. And so this is the inclination of the large-scale uniform field, in a sense. And this value of B with the dotted lines is the one obtained from the map for DN31. And this line here is coming from the simulation. So from the analysis of the map, the turbulent information from the dispersion of the angle as a function of the inclination of the uniform magnetic field. And so for DN31, we see that there is a regime where we can recover the turbulent information that we've got from the observed maps. And this, for the 4 regions, we are able to find some regimes here. And this is quite exciting, because this tells us something about the physics of the cloud, and we can reproduce these variables. And now if we look to the polarization degree, which is related to the efficiency to align grains, and how the turbulence will combine, mitigate the field lines, for the same parameter, the inclination angle of the uniform field in the cubes, we see that, as I was mentioning, if the uniform field is in that direction, in front of the observer, we will see mainly the turbulent component. So the polarization degree is very low because there is a mix of information along the line of sight. And if the field starts to be more and more into the plane of sky, we will see that the polarization efficiency increase because we can see more and more aligned grains by the uniform field. And in this case, with polarization efficiencies of 10 or 12%, so the dark or the gray line, we are also able to define a regime which is comparable to the dotted lines obtained from the observed maps, and this for the 4 regions as well. And so over the 3 parameters, the polarization parameter, the turbulence parameter, which I call B, and the mean degree of polarization, we can fit 2 of the 3 parameters for the envelopes of the clouds. And so interesting part is that, just an aparte, is that from a completely independent method, Martin Wood and collaborators, they've developed from about 2000 some people were seeing some difference of in the spectrums of ions and molecules of similar masses. They were seeing different wings into the spectrum. And so the idea is that if you've got a partially ionized medium and with a uniform field which is dominating over the turbulence, the ions will see the magnetic field. There are flows into the molecular cloud, but the neutrals will go straight. So this difference of dispersion into the lines of the ions and the neutrals theoretically can give us information with a simple model about the structure and the mean inclination of the uniform field, in a sense. So this is an independent method. And at the end, if we compare, so if we make a compilation of all that I discussed before, so from the simulations with a polarization efficiency of 10% for the 4 regions that we discussed, so we can define a mean inclination angle range for the uniform component of the field. And so we've got constraints from so those plots, basically. And from the method just before, which is a comparison of ions and neutral velocity lines, we've got information about the magnetic field, large-scale structure of the field inclination and its inclination angle with respect to the field line for MC23 and the DR21. And if we combine the Zeeman measurements with Chandrasekhar and Fermi method, so Chandrasekhar and Fermi method, we've got an estimate of the field, uniform field in the plane of sky, the intensity of the field. So Zeeman is along the line of sight. We've got a constraint on the inclination angle of the magnetic field. And so by combining, the first point is that each time we've got a possibility, a range of solution when we combine every method. And if we combine all the results at the end, we've got constraints on the large-scale uniform field, which will dominate over the medium. And so that's the conclusion of the talk, is that with simple isothermal and non-ideal 3D MHD simulation, so we can recover 2 parameters over 3 because of the physics used into the models. So we don't have gravitational effects into the simulations. That's why we avoid to include the cores, the physics of the cores. There is no ambipolar diffusion as well, meaning that we don't consider that the ions can see the magnetic fields, and that there will be possibility of collisions between the neutral and the ions, and so coupling between the neutrals and the magnetic field. And we use simple models for those grains. But the interesting part is that we are able to recover the MHD regimes in terms of Alvenic Mach number and sonic Mach numbers, consistent with the Zeeman measurements. And we are able to get information about the inclination of the mean inclination of the large-scale magnetic field by comparing with other methods. And that's it.
Thank you very much. Time for questions?
What is the spatial resolution of your polarimeter on the molecular clouds?
It's 40 arc seconds.
How will you extend your research in the next year? Is there any way that the lower resolution, spatial resolution data of Quixote can help to better understand the distribution of the magnetic field in these structures?
So those are something I started to think about, because we know that we've got very tiny small grains producing anomalous wave, anomalous microwave emission, which can be polarized. And one question is that where are those small tiny grains located with respect to the molecular clouds for those regions, for example? And do they see the large-scale structure of the field? So if we know the inclination of the large-scale structure of the field, is there a link between these very tiny dust grains, this polarized alignment, and what we see from bigger dust grains distributions? So it's not completely clear. I know some people started to look at polarization from starlight. We discussed with Ricardo about it, and anomalous wave emission, I think. So there are probably a lot of things to explore, because from the diffuse interstellar medium to the denser regions of the cloud, people believe, and apparently we've got proof of this, that we've got coagulation processes. So the small grains will probably very less likely be into the denser regions. But how is it at the interface between the clouds? It's not clear actually. So it's opened a lot of interesting questions.
How well do your results agree with the assumption of equipartition of magnetic and kinetic energy in the clouds?
So the physics use, I didn't mention this physics used into the MEG simulations agree with equipartition. It's been shown, it's been discussed in the 2008 paper.
So the magnetic energy is approximately the same as the kinetic energy?
Yes. Yeah. There is no inconsistency with this aspect.
No more questions? Okay, then let's thank Frederick again.